In this video, we're going to look at a couple of integrals that use the basic rules. They just might not be really obvious about which rule you're going to be using. So for this first example, I've got the integral of 1 over 1 plus e to the x dx. Now, a lot of you will try right off the bat and make u 1 plus e to the x. And that would be a valid approach, except the problem with that would be that if we take u prime, that would be 0 plus e to the x. And we don't have that as it stands. We know that we can't multiply on the outside by an e to the x. So we can't do that. There's no way we can just multiply by e to the x over e to the x. What we can do is add and subtract the same thing on the inside of the integral. So what I'm going to do is I'm going to add e to the x and subtract e to the x. So by doing that, I haven't changed anything about the integral. Now the trick here is that I'm going to group it like this. I'm going to say 1 plus e to the x for the first integral, and then we're going to split it at that minus sign. So what I'll end up with is the integral of 1 plus e to the x over 1 plus e to the x dx minus the integral of e to the x over 1 plus e to the x dx. Now what's cool about this is this cancels and you just have the integral of 1 dx. With this one, we now have our du over u, or u prime over u dx, whichever way you want to think about it. We have our du over u. So here, this is just going to be x. This will be the natural log of the absolute value of u plus c. And of course, the u here is 1 plus e to the x. So we end up with x minus the natural log of the absolute value of 1 plus e to the x, all plus c. And you don't technically need the absolute value bars here. You could remove them, or if you're not sure about it, you can leave it. This is another example of one where the rule that you need to use might not be super obvious at first. And I might try a couple of different things before I figure out really what I want to do. But I do notice that I have a natural log of cosine of x and I have a tangent of x. So I can't just use it's kind of hard to say. But with this one, if I recognize that if I let u be the natural log of the cosine of x, and I find a u prime using a chain rule here, w would be cosine of x, w prime would be negative sine of x. So if I let this be the natural log of w here, then u prime would be w prime over w, which would be negative sine of x over cosine of x, which would be negative tangent of x. So to start on my actual problem, I'm going to reorder this. I've got the natural log of cosine of x times the tangent of x dx. In order to have the u prime I need here, I need a negative sign, which means I can put one out front. This actually becomes negative integral of u du. This is my du. This is my u. So this is actually a power rule. This will be negative u. This is the first power, so we'll have 1 plus 1, and then we'll have 1 plus 1 in the denominator. And that's going to be all plus c. So we get negative u squared over 2 plus c. And when I plug in the u, I'm going to bring the 1/2 out front. So we'll have negative 1/2. We'll have the natural log of cosine of x squared, all plus c. So this is just a complicated power rule, but that's one of the first integrals we learned. The hardest part was just figuring out what your c is. You may also have some problems where you have to use some clever trig identities in order to evaluate an integral. I've got the integral of cotangent squared of 3x dx. So if I go back to my list from the beginning of the section, I notice that I don't have a rule for cotangent squared. I do have a rule for secant squared and a rule for cosecant squared, but I don't have a rule for cotangent squared. So I can relate cotangent squared and cosecant squared using what's called the Pythagorean identity. So the Pythagorean identity, the version of it that you're probably the most familiar with is sine squared of theta plus cosine squared of theta equals 1. Now, in order to convert this to cotangent squared instead of sine and cosine squared, what I would do is I would take all of these pieces and I would divide every single piece by sine squared of theta. So I would get 1 plus cotangent squared of theta equals cosecant squared of theta. And since I have a cotangent squared here, I'll subtract 1 and get cotangent squared of theta equals cosecant squared of theta minus 1. And you can do a similar thing for the secant and tangent version. You would just multiply through by 1 over cosine squared instead of sine squared. So coming back to my original problem, I can now take, instead of cotangent squared of 3x, I can write this as the integral of cosecant squared of 3x minus 1 with respect to x. I can split that into two separate integrals. So I have the integral of cosecant squared of 3x dx minus the integral of 1 dx. On this left integral, I can let u be 3x, so u prime would be 3, and du would be 3 dx, so I need a 3 and a 1/3. I would have 1/3 times the integral of cosecant squared of u du, and then of course this one is just x plus c. And if I look back at my list now, I know that the integral of cosecant squared of u is negative cotangent of u plus c. So I will have 1/3 times negative cotangent of u. And if I plug the u back in, I just have negative 1/3 cotangent of 3x minus x plus c. And that will be my final answer. So the take home from this is everything in this section is going to use the basic integration techniques that you've learned in Calculus 1. You just may have to apply them a little bit differently, or you may have to use a little bit of algebra or trig to get you to the point where you can apply them. So look at what you have and try to figure out how you can use the valid algebra and trig rules to sculpt your expression into an expression that matches one of these basic 20 integration rules.